All right, so now we are going to talk about some substitutions. When we have equations that are not nice in the sense that we don't have a technique to solve them, but they look kind of like maybe we should be able to solve them. Sometimes we can make a substitution. So like we've just been talking about, solving differential equations is a lot like integrating. It's recognizing patterns, recognizing forms. Oh, this looks like this type of thing. Can I do this? But often, like with integration, you try something and it's like, oh, that wasn't a trig sub. What do I do now? This is, for some equations, this is the what do we do now. So the first type of substitution we're going to talk about has to do with equations that we call homogeneous. And we'll talk about a different homogeneous equations in a different context when we talk about higher order differential equations. All right, so we're going to say a function f of xy, and it needs this particular property. That f of tx comma ty equals t to the alpha f of xy. So substituting in tx and ty, after doing that and performing whatever the function tells us to do, we can factor out some power of t out of the original function. We call that equation, or that function, homogeneous. I'm going to say for some real number alpha, and we say with degree alpha. So for example, f of xy equals x squared plus y squared. F of tx, ty is tx squared plus ty squared, ty squared, which we can write as t squared times x squared plus y squared. I can factor out that t squared. So that function, f of xy equals x squared plus y squared, is homogeneous with degree 2. But f of xy equals x squared plus y squared plus 1 is not homogeneous. That plus 1 makes it so we can't factor out that t squared if we put in a tx and ty. So we're going to be interested in differential equations where that look in the form that we just talked about with our exact equations, where our component functions are both homogeneous. Differential equation mxy dx plus n xy dy equals 0 is homogeneous if both m and n are homogeneous with the same degree. So that means m of tx ty equals t to the alpha m of xy, and n of tx ty equals t to the alpha n of xy. If this is the case, we can write m of xy equals x to the alpha times m of 1 comma u, and n of xy equals x to the alpha n of 1u, where u equals y over x. And let me go back to our example. X squared plus y squared we can write as x squared times 1 plus y over x squared. So this is what we're doing to our functions. If our functions are homogeneous, we can rearrange them this way. And similarly, we could say m of xy equals y to the alpha v comma 1 and n of xy equals y to the alpha n of v comma 1, where v is x over y. So this suggests the substitution I'm going to say substitutions. Y equals ux from here, or x equals vy from here, to solve these. Making these substitutions transforms our homogeneous equation into separable differential equations. So we go from a homogeneous equation to a separable equation. So we're transforming our variables now from x and y to u and v, and we have a separable equation that we can then solve for u or v, and then we can back substitute to solve for x and y. From using these substitutions and our original equation, it's really not difficult to rewrite the differential equation in separable form. So if you want an interesting little challenge, start from one of these substitutions in your original equation, and you take the derivative of x, or the derivative of y. Is you're going to use the product rule here, make your substitutions, and it's not hard to see that you end up with a separable differential equation. So if you want an interesting little challenge, I would suggest you give that a try. All right, so I want to talk about the technique now. So first we need to determine if the equation is homogeneous. This substitution only works if our equation is homogeneous. If so, we make the substitution. X equals Vy, or y equals ux. We can make either one. Either one will work. We substitute and rewrite in separable form. Then we solve for u or v, because u or v is going to be our new variable. And then we back substitute to solve for x or y. All right, so let's look at an example. We want to solve y squared plus xy dx plus x squared dy equals 0. Now we might look at this one and say, oh, maybe this one's exact. But we can see the partial of this with respect to y is not going to be the partial of this with respect to x. So it's not going to be exact. We possibly could try an integrating factor. That would be something to try. But we can also look and see if this is homogeneous. Ty squared plus tx times ty is t squared times y squared plus xy, and tx squared is t squared x squared. So our equation is homogeneous. And our degree is 2. And for this one, just because, I don't know why, I just chose y equals ux. Sometimes, depending on the substitution you make, the integration can be easier, and not just because. I'll go back. It's not just because that I chose. Here, y is x. This function in front of the dy is x squared. I thought, well, that's a simpler function, so maybe substituting y equals ux. That's going to be easier than make a nicer substitution than that one. That's just kind of the thought process that went through my head. So dy, we need to substitute for dy also. dy is going to be u dx plus x du using the product rule. So now I'm going to substitute into the equation. So I have ux squared plus u x times x, making everything explicit here, dx plus x squared times dy, u dx plus x du equals 0. Now I'm going to multiply through and combine like terms, get all my du's together, get all my dx's together, and I get u squared x squared plus 2ux squared dx equals x to the third, sorry, plus x to the third du equals 0. I'm going to factor out an x squared here and divide. So I have an x squared here that I can divide by. So I get u squared plus 2u dx equals, or sorry, plus x du equals 0. Well, this is just a function of u. This is just a function of x, so I can separate the variables. And I get dx over x plus du over u squared plus 2u equals 0. We could just integrate now and integrate term by term. That would be fine. I chose to rewrite this as dx over x equals negative du over u squared plus 2u. Uh-oh, what do we got going here? That's a partial fractions. I'm not going to go through all the algebra, but I'm going to say that this equals negative integral 1/2 over u minus 1/2 over u plus 2 du. So that's a partial fractions. So we end up with, when we integrate here, we get the natural log of x equals negative 1/2 natural log of u minus 1/2 natural log of u plus 2 sorry, this is a negative out front, there we go, plus c. And now I'm going to substitute back in, so the natural log of x equals negative 1/2 natural log y over x plus 1/2 natural log y over x plus 2 plus c. And I combine these, so the natural log of x equals the natural log of the square root, the 1/2, y over x plus 2 over y over x, and the square root takes all of that in, plus c. And then we can rewrite that, we can exponentiate both sides, and I wrote x equals c times, or I'll say c1, c1 times the square root. If I rewrite all of this, find a common denominator, I get y plus 2x over y. There are other ways we could write this, but we will have an implicit solution for this one. So either substitution we can use. One may make the equation nicer. If the integrals that you end up with at the end are difficult or impossible, you end up with partial fractions and you don't like partial fractions, you can go back and try the other substitution. Maybe that'll make it nicer. Yes?
Would the other substitution give us a function y equals, or is that?
Yes, I think you'd probably get your solution would look different, but it would be equivalent. All right, questions there. Next substitution is Bernoulli differential equations. Bernoulli differential equations are almost first-order linear differential equations. They look like this: dy dx plus p of x y equals f of x times y to the n. This y to the n makes it nonlinear. Now, I'm going to say for n not equal to 0 or 1. If n equals 0, the equation is linear. Because then we just have dy dx equals p of x y plus p of x y equals f of x. And we can find our integrating factor and solve that. If y equals 1, or sorry, if n equals 1, the equation is separable. Because then we could divide by this y would go away. I'd have dy over y equals and p of x dx plus f of, or minus f of x dx. So I'd have all the x's together and all the y's together. If n is not equal to 0 or 1, we make the substitution z equals y to the 1 minus n. And by doing this, we can change it into a separable, sorry, a first order linear. And I've always used z for this substitution in Bernoulli equations. I think our book uses a different variable. They might use t, I can't remember. But I've always used z, so I'm going to use z because then I might, if I don't, then I might switch the variables and confuse people. So I just want to do an example to illustrate the technique. So we don't, now we make this substitution. This is not the quantity that we multiply by. So let's look at an example. So dy dx minus y equals e to the x y squared. So that y squared makes this a nonlinear equation. Here n equals 2. It's whatever this exponent is when we write our equation in standard form. N equals 2. So I'm going to say z equals y to the 1 minus 2 is y to the negative 1. And then dz is negative y to the negative 2 dy. Or let me write it this way, z prime dz dy is negative y to the negative 2 dy. We are going to multiply through by this. Negative y to the negative 2. So I'm going to multiply. I get negative negative y to the negative 2 y prime plus y to the negative 2 y equals e to the x, negative e to the x. Well, I can rewrite this as negative y to the negative 2 y prime plus y to the minus 1 equals minus e to the x. This is z prime. This is z. So z prime plus z equals minus e to the minus x. This is a first order linear equation. In z now. So we can solve this equation for z, and then once we find z, we can back substitute to find y. So multiplying through by this quantity transforms our equation into a first order linear equation with our new variable z. So p of x here is just 1. So our integrating factor is mu of x equals e to the integral of 1 dx, which is e to the x. So now we multiply through our new equation by the integrating factor. So I get e to the x z prime plus e to the x z equals minus e to the 2x. Well, now the left-hand side is a derivative of a product. That's the purpose of the integrating factor. This is e to the x z prime equals minus e to the 2x. We integrate both sides. So e to the x z equals negative integral e to the 2x dx plus our constant of integration. Account for that explicitly. So e to the x z equals minus 1/2 e to the 2x plus c. Z equals minus 1/2 e to the x, dividing through by e to the x, plus c e to the negative x. And this is y to the minus 1. Minus 1/2 e to the x plus c e to the minus x. So y equals 1 over this whole thing. And we have our solution. And if we look back at our original equation, there's our original equation, y equals 0 is a singular solution. Because we plug in y equals 0, the derivative is 0, 0 plus 0 minus 0 equals 0. We would not get y equals 0 from plugging in some value for that constant. questions on Bernoulli equations? Okay, our final substitution. I think this is the easiest substitution that we talk about. Or the nicest, easiest, nicest, some combination of those. Any differential equation in the form dy dx equals f of ax plus by plus c. Some linear function of x and y. So the derivative of y with respect to x is some function of linear functions of x and y. Can be made separable by substituting u equals the thing in the parentheses here. And we need b not to be 0. So we need y in this function here. So making this substitution makes our equation separable. So example, dy dx equals sine of x plus y. Not a super complicated function, not a super complicated differential equation. But if we, without this technique, maybe more complicated. So this is just some function of a linear function of x and y. So f of xy is just sine of x plus y. So I'm going to let u equals x plus y. Du dx, I need to take the derivative here because u becomes my new variable. Du dx is 1 plus dy dx. I'm just taking the derivative of this with respect to x. Yes?
Does it matter whether you do du dx or du dy?
Yeah, you could do y and then solve, then you'd get you'd get y in terms of u though. What we want, and u, I guess it wouldn't matter. I think we usually do with respect to x because usually we take the derivative with respect to x. And then dy dx is du dx minus 1. That's another reason we substitute this way, is so we can just plug in for dy dx. So we get du dx minus 1 equals the sine of u. And I can separate this. I can add 1 to both sides. So I get du over the sine of u plus 1 equals dx. And we're going to integrate. So we get the integral of du over sine u plus 1 equals x, and I'll account for my constant there. This was a fun integral. Didn't we do this one, integral of the day, the other day? Last week? Sine, yeah, multiply by sine minus 1 over sine minus 1. So multiply by a convenient form of 1. So we get the integral of sine u minus 1 du over cosine squared u equals x plus c. And then what do we do here? Yeah, separate it into two fractions. So we get sine u over cosine squared u minus 1 over cosine squared u, which we can write as secant u tangent u. One of the sine u over cosine u is the tangent, 1 over cosine is the secant, minus secant squared u du equals x plus c. And these are nice known integrals. Secant u minus tangent u equals x plus c. Finally back substitute, and we get secant x plus y minus tangent of x plus y, back substituting, equals x plus c. And you could probably do some other work with, there are sum to product and product to sum formulas that you could use there, maybe. But I think you do a lot of work for not much gain. That one's fun. Those are fun, I think. All right, so we have homogeneous equations, substitution for homogeneous equations, substitution for Bernoulli equations, and substitution for functions of linear equations of x and y. And then we will have all of our first order differential equation solution techniques. Next chapter we'll start talking about higher order differential equations. Lots of fun stuff comes up then. And what are we